The dark story behind the Cooper-Bessemer GMV, the engine that moved America's gas and was buried. Two brothers started a company in Ohio with $50 from the sale of a horse. 103 years later, the engine their company built was quietly running the entire American natural gas pipeline system. Then the company grew up, moved away, and changed its name until nobody recognized it anymore. The engine kept going. Some of them are still running today. In fields, alone, in the dark. Mount Vernon, Ohio, 1936, population around 8,000 people. Nobody outside of Knox County had heard of it, and most people inside Knox County had never left it. But there was a factory on North Sandusky Street that built things the whole world needed. It started, as most great American stories do, with almost nothing. It's 1833. Charles and Elias Cooper were two brothers from a farm south of town. They wanted to open a foundry. Between them, they had one surplus horse. They sold it. $50. That was the startup capital for what would eventually become one of the most consequential industrial companies in American history. For the first few decades, they made plows and kettles and iron stoves, standard foundry work. Then they noticed something. Steam engines were everywhere, and the good ones were scarce. By the 1860s, they were building coreless steam engines, the large industrial kind that powered mills and factories across the Midwest. By the 1870s, they had produced what was essentially the first commercially viable American farm tractor. And the Cooper Company kept finding the next thing before everyone else did. The next thing, in the early 1900s, was natural gas. There were deposits everywhere in the American Midwest, and nobody had figured out how to move the stuff efficiently over long distances. You needed pressure. To maintain pressure over hundreds of miles of pipe, you needed compressor stations. And to run those compressors, you needed engines. Powerful, reliable, slow-speed engines that could run continuously without breaking down for years at a time in a field somewhere with minimal supervision. Cooper was building exactly those engines, and they were getting good at it. In 1929, the C&G Cooper Company merged with the Bessemer Gas Engine Company of Grove City, Pennsylvania. Cooper needed more production capacity. Bessemer needed capital. Both had been posting nearly identical earnings for 3 years. It was a clean match. The new company was called Cooper-Bessemer Corporation. They listed on the American Stock Exchange. They were, briefly, the largest builder of gas engines and compressors in the country. Then the stock market crashed in October of that same year, and they went from the largest builder in the country to barely surviving. For a while, you could walk up to the factory in Mount Vernon and run a machine for $5 a day if something broke down. That was the Great Depression at Cooper-Bessemer. Sales dropped more than 90%. The plant shut completely for months. But they survived it, and what came next was the engine that made everything. We cover stories like this every week. Engines, factories, and machines that built the modern world and got forgotten. If you're not subscribed yet, now is a good time. There is a lot more of this story left. Here is the problem that a man named Ralph Boyer was trying to solve in the middle of the 1930s. Natural gas was abundant in America. The Midwest and the South were full of it. The Northeast needed it. The coasts needed it. Moving it from one place to the other required pipelines, and pipelines required compression. Without compressor stations placed every 50 to 100 miles along the route, the gas simply stopped moving. The pressure bled off, the flow rate dropped, and the pipe became useless. The compressor station was the answer. A building somewhere in a field, housing an engine powerful enough to take the gas at whatever pressure arrived from the previous station. I boost it back to pipeline pressure and send it on its way. That engine had to run continuously, not when someone felt like turning it on. Continuously. 24 hours a day, 7 days a week, 365 days a year, sometimes for years, without stopping. The existing compressor engine designs in the 1930s were not built for that. They were large, they were complicated, they had too many parts that could fail, and they were not efficient enough for the economics of long-distance pipeline operation. Pipeline companies were building infrastructure worth tens of millions of dollars. They were not going to stake that investment on a machine that needed constant attention. Boyer's assignment was to design something that didn't break down, something compact, something efficient, because gas engines running continuously consumed enormous amounts of fuel, something simple enough to be maintained by mechanics in a field, not engineers in a laboratory, and something reliable enough to run for decades without fundamental revision. He had joined Cooper-Bessemer in 1926, and he would spend the next 4 decades there. The GMV was his answer. It was not a quick answer, and it came with consequences nobody saw at the time. The Bessemer merger in 1929 gave Boyer something he needed. Not just additional factory floor space. It gave him access to the Bessemer Gas Engine Company's engineering heritage. Bessemer had been building gas engines since the 1890s. Their people had spent 30 years learning what worked and what failed in continuous duty industrial applications. When the two companies merged, that accumulated knowledge came with them. Boyer spent the early 1930s experimenting. The fundamental challenge was mechanical. A gas engine and a gas compressor are very different things. An engine takes fuel and produces rotation. A compressor takes rotation and produces pressure. To combine them into a single unit, you had to make one machine do both jobs simultaneously, from the same crankshaft, using the same power strokes. The standard approach at the time was to run compressor piston rods side by side with power piston rods, all attached to the crankshaft in separate throws. It worked. It was also bulky, generated high bearing loads, and had more moving parts than necessary. Boyer thought there was a better way. His solution was the articulated connecting rod arrangement. Instead of running power and compressor rods in parallel, he designed them to share a single master rod. 2 power piston connecting rods drove onto one master compressor rod for each throw of the crankshaft. The angle between the engine cylinders and compressor cylinders formed a V-shape, compact, mechanically efficient, and with significantly lower bearing loads than the side-by-side approach. Lower bearing loads meant less wear. Less wear meant longer service life. Longer service life meant exactly what pipeline companies were asking for. Boyer had the design, he had the factory, he had the backing of the merged company. The first GMV units came out of the Mount Vernon plant in 1936. They ran, and then they ran some more, without stopping, without complaint. Cooper-Bessemer built them in 4-cylinder, 6-cylinder, or 8-cylinder, and 10-cylinder configurations, 4 cylinders to 10. Each cylinder was 14 inches across and 14 3/4 inches of stroke. The engine turned at 300 revolutions per minute. Slow, deliberately slow. At 300 revolutions per minute, the bearings barely worked up a sweat. The valve gear barely noticed. The entire machine operated at a pace that, compared to automotive engines, seemed almost leisurely. That was the point entirely. The 1940s brought something Boyer and the Cooper-Bessemer engineers did not anticipate: World War II. The factory on North Sandusky Street pivoted almost overnight. The plant started building marine diesel engines for the U.S. Navy. They powered minesweepers. They powered tugboats. They powered rescue boats and patrol craft. They powered Liberty ships, those mass-produced cargo vessels that carried 75% of the material the Allied forces moved across the Atlantic. Cooper-Bessemer earned both the Maritime M Award and the Army-Navy E Award for wartime production excellence. Outstanding achievement. When the war ended in 1945, the world changed fast. American soldiers came home and did what soldiers always do. They started families. They moved to the suburbs. They bought houses. They wanted heat and hot water and modern appliances. Demand for natural gas exploded, not increased. Exploded. Between 1945 and 1965, consumer demand for natural gas more than doubled in the United States. The existing pipeline network was nowhere near large enough to handle it. About half of all the natural gas pipelines that exist in the United States today were built in the 1950s and 1960s. Roughly 300,000 miles of interstate and intrastate pipeline went into the ground during a 20-year window right after the war. In 1954 alone, American utilities were adding 800,000 new gas customers every year. By 1957, natural gas was providing nearly 23% of the nation's total energy supply, up from 12.6% in 1945. Every single mile of new pipeline needed compressor stations. Every compressor station needed engines. The GMV was ready. Orders flooded in. The Mount Vernon factory ran flat out. At its peak in 1963, a Cooper-Bessemer employed 2,400 workers at the Mount Vernon campus. The town of 8,000 people had a factory that employed roughly a third of the entire population. As one longtime employee later remembered, everybody in Mount Vernon worked at Cooper once back in the olden days. Another said if you didn't like your boss, you could quit and have another job by 4 p.m. the same day. The GMV went everywhere. Not just across America. The engines were licensed for manufacture in Russia, Ireland, France, Germany, the United Kingdom, Japan, Italy, and Mexico. They were installed in 43 countries. Whatever language you spoke, if you were moving natural gas through a pipeline, you almost certainly had a Cooper-Bessemer on your property. And then General Electric showed up. In the 1950s, GE had developed combustion gas turbines for industrial pipeline use. The appeal was real. Turbines ran at higher speeds, could drive high-speed centrifugal compressors, and were better matched to the scale of newer, larger pipelines. El Paso Pipeline Company purchased 19 GE turbine-driven centrifugal compressors for its Southwest pipeline. Other companies watched. Then they followed. Boyer saw the threat clearly. He said so, in retrospect, plainly. He later stated that the only way he could see to beat the gas turbines in a reasonable time was with a piston engine. He also admitted that was a serious mistake. The company president, he recalled, came to his desk every single day asking the same question. What the hell are you doing about a gas turbine engine? Boyer, who had spent his entire career building piston engines, tried to answer with a piston engine. Cooper-Bessemer spent the early 1950s developing a free piston engine in conjunction with the U.S. Navy, a genuinely innovative concept involving opposed pistons with no crankshaft, generating hot gas to drive a turbine. Test units produced the equivalent of 1,750 horsepower at 45% thermal efficiency, impressive numbers. But without a crankshaft controlling piston position, keeping the pistons from destroying themselves at the end of each stroke was extraordinarily difficult. If combustion timing slipped, the engine didn't stumble. It stopped, dead. The development program eventually died without producing a practical commercial machine. In 1960, Cooper-Bessemer introduced the world's first industrial jet-powered gas turbine, a two-stage centrifugal pipeline booster driven by a Cooper-Bessemer power turbine using exhaust energy from a Pratt and Whitney aircraft jet engine. It worked. It was a real product. But GE had a years-long head start, and the pipeline market had already made its preferences clear. Cooper-Bessemer never caught them. Meanwhile, the GMV just kept running. Now let's talk about what the GMV actually was, mechanically, and why it held up for half a century in conditions that would have destroyed lesser machines. Start with the basics. The GMV was a two-stroke engine, not in the way a chainsaw is a two-stroke. This was a large-bore, slow-speed industrial two-stroke running on pipeline natural gas. A two-stroke means the power stroke and the exhaust and intake cycle happen once per revolution. Every revolution is a working revolution. Compare that to a four-stroke automotive engine, where every other revolution is the one that generates power. The GMV worked on every turn of the crank at 300 RPM, that's 300 power strokes per minute per cylinder. Your car at highway cruise turns between 2,000 and 2,500 revolutions per minute, but only gets half those revolutions as power strokes. The GMV ran slower and worked harder in the most productive sense of that phrase. The cylinder dimensions: 14 inches of bore, 14 3/4 inches of stroke. That is a cylinder more than a foot in diameter, with a piston traveling more than a foot on every revolution. The swept volume per cylinder, the volume of gas displaced in each power stroke, was enormous. On a GMV-10, you had 10 of those cylinders firing in sequence. The machine weighed around 70,000 pounds in its four-cylinder configuration. That is 35 tons for the smallest version of the lineup. It was not a machine you moved. The integral design was the key breakthrough. Standard compression setups of the era used a separate engine driving a separate compressor through a mechanical coupling, 2 frames, 2 lubrication systems, 2 sets of bearings. The coupling itself was an additional complexity and a potential failure point. Boyer eliminated all of that. The compressor was part of the engine. One machine, one crankshaft, one frame. The compressor cylinders that actually pushed gas through the pipeline were mounted on the same crankshaft throws as the power cylinders, linked through the articulated rod system. That articulated rod arrangement deserves a second look. 2 power piston rods sharing one master compressor rod per crankshaft throw. The load path through the master rod was direct and efficient. The V-angle between engine and compressor cylinder banks, chosen to optimize bearing loads at operating speed, kept the forces on each crankshaft bearing well within the material limits of the day. Boyer and his team worked out that angle geometry using slide rules. No finite element analysis, no computer models, engineering judgment based on decades of experience, and it worked essentially without revision for more than 50 years. On the scavenging system, how the engine cleared exhaust gases and charged fresh air into the cylinder between strokes, evolved significantly over the production run. Early GMVs used mechanically driven scavenging via piston-assisted flow. Later variants added external blowers, then turbochargers. Each upgrade improved thermal efficiency and increased specific power per cylinder. Boyer later said the GMV was the most responsive engine in the lineup to scavenging improvements. Each upgrade in airflow management produced measurable output gains without requiring any change to the fundamental engine architecture. Over the 55-year production run, these incremental gains roughly double the power output from the original 1936 specification. Same bore, same stroke, same crankshaft geometry, twice the output. That is what systematic engineering improvement looks like when the underlying design is genuinely sound. The clean burn system introduced after 1978 added electronic control of air-fuel ratio and ignition timing to the GMV design. The effect on nitrous oxide emissions was dramatic, enough to meet California's emission standards, which were at the time the most restrictive in the country. The same basic machine that Boyer had designed in the mid-1930s, now with electronic controls, was meeting late 1970s environmental regulations. That should not have been possible. It was. The fuel source is worth noting. The GMV ran on pipeline natural gas, the same gas it was compressing. Approximately 2 to 3% of the gas flowing through each station was consumed as engine fuel, and the machine was, in a sense, eating a fraction of its own product to do its job. This was economically straightforward and operationally convenient. It also meant the engine and the pipeline were inseparable. The GMV did not exist alongside the gas transmission system. It was part of it. Remove the engine, and the gas stopped moving. The sound of a running GMV became part of the professional identity of pipeline mechanics who worked around them. At 300 RPM, the exhaust pulses are slow enough that you can hear each one individually, a deep rhythmic percussion that vibrates the floor of the compressor building. Experienced operators could tell by ear whether an engine was running correctly. A change in note meant something. A change in vibration pattern meant something. The machine communicated through physical sensation, and the people who tended them learned to listen. That relationship between operator and machine is gone now. The people who knew how to hear it have mostly retired. The GMV did what it was designed to do. It ran the American natural gas network through the biggest peacetime infrastructure build-out in the country's history. While politicians and planners and developers got the attention, the actual mechanical work of moving gas from the ground to people's homes was done mostly by this engine, in a building, in a field, that almost nobody knew existed. But Boyer's GE problem never went away. By the early 1960s, it was clear that the future of large-scale pipeline compression belonged to turbines and high-speed centrifugal compressors, not because the GMV failed. Because the scale of new pipeline projects exceeded what piston engines could practically address. The GMV was optimal for stations requiring up to several thousand horsepower. The next generation of pipelines wanted more than that. In configurations, the integral engine compressor was not suited to provide. Cooper-Bessemer adapted. By the mid-1960s, company revenue had grown from $68 million to $117 million annually. It had become a large and increasingly diversified industrial corporation, too diversified and too large, some argued, to remain headquartered in a small Ohio town. In December 1965, the company changed its name to Cooper Industries, reflecting how far it had grown beyond gas engines and compressors. 2 years later, the headquarters moved from the floor above the First National Bank in downtown Mount Vernon to Houston, Texas, the geographic mainstream of American business, as the annual report called it. That phrase did not mention what it was leaving behind. On January 31, 1968, Charles G. Cooper retired. He was the grandson of co-founder Elias Cooper. His retirement ended 134 years of Cooper family involvement in the company that started with the proceeds from a horse. Nobody marked the moment particularly. It was just a retirement. The Mount Vernon plant continued producing. The GMV continued being built through the 1970s. But the decisions were being made in Houston, and the people making them were looking at the whole portfolio: hand tool companies, electrical equipment manufacturers, hardware brands, not specifically at the engine that had built the company. The gas and diesel engine business became one line item among many. Its share of revenue declined steadily. In 1995, Cooper Industries spun off its petroleum and industrial equipment group as Cooper-Cameron Corporation. The Mount Vernon plant came with that spin-off. In 1999, Cooper-Cameron sold its rotating compressor business to Rolls-Royce for approximately $200 million. The Cooper name left Mount Vernon's factory signage for good. Rolls-Royce employed around 1,200 workers when they took over. They said the right things. Local officials said the right things. Things continued for a while. Then the layoffs began. Slowly at first, then not slowly. Over 13 years. Rolls-Royce reduced the workforce by nearly half. By 2014, when Rolls-Royce sold the plant to Siemens for $1.3 billion, only 675 workers remained. 6 weeks after the Siemens signs went up, Siemens announced it was laying off 25 to 30% of the remaining workforce. In 2016, assembly and test activities transferred out of Mount Vernon entirely. In 2018, Siemens announced the final closure. 400 people lost their jobs on September 30th of that year. The mayor called it a pretty big hit. That was not an overstatement. The 47-acre campus on North Sandusky Street eventually came to the Knox County Land Bank. In 2020, they renamed it Cooper Progress Park, a name on a sign, and a parking lot where the machines used to be. The Cooper old-timers, former employees who had been gathering for an annual potluck every summer since 1999, held what they knew would be their last reunion in 2023. In the early years, those reunions drew around 400 people. By the final gathering, 140 came. Many had traveled from California, Texas, Oklahoma. They sat in the Knox County Historical Society building, in a room with a 70,000-pound engine in it, and talked about the place that had been the center of their working lives. Here is where the story gets genuinely strange. The engine outlasted the company. The GMV production run ended. The factory moved on. The corporate name changed 4 times. The physical plant became a parking lot. Nay, but the engines were still in the ground, still connected to pipelines, still turning over at 300 revolutions per minute in compressor stations from Louisiana to Kansas to Pennsylvania to the Pacific Northwest. As of the most recent pipeline industry assessments, more than 2,000 GMV model engines were still actively operating in the American natural gas transmission system. Some of those machines were manufactured in the 1940s. They have been running continuously, with maintenance, with component replacements, with the occasional field repair using fabricated parts for 80-plus years. No fundamental redesign, no replacement of the basic mechanical architecture that Boyer drew up on a drafting table in Mount Vernon, Ohio, in the 1930s. The American Society of Mechanical Engineers designated the GMV a historic mechanical engineering landmark in 2006. The designation plaque sits in the Knox County Historical Society Museum next to the actual GMV-4, built in 1944, operated until 2002, and still capable of running today. It weighs 70,000 pounds, and it fits in a museum. The remaining fleet now faces a different kind of challenge. Modern EPA regulations on stationary reciprocating engines target both nitrous oxide and unburned methane. Methane is a greenhouse gas roughly 28 times more potent than carbon dioxide, and the 2-stroke combustion cycle of the GMV produces measurable methane slip, unburned gas escaping without being oxidized. Colorado State University currently operates a GMV test engine specifically to research emission reduction techniques. Results suggest high-pressure direct fuel injection and optimized timing can cut methane emissions by roughly 50%. Whether that is enough to keep 2,000 aging engines running under tightening future standards is an open question. Replacing a GMV means replacing the foundation, the building, and the entire compression system around it. Not cheap. Upgrading an existing engine with modern controls costs less. Pipeline operators are running both calculations, and the answer differs at every station. The machine that built modern American energy infrastructure is itself now in need of a plan. 2 brothers sold a horse and built a foundry. 100 years later, a man named Ralph Boyer designed an engine in that same Ohio town, and that engine heated American homes for the next 50 years without anyone outside the industry knowing it existed. The company grew up and moved to Houston, and changed its name and its priorities and eventually its identity. The factory got sold to a British company and then to a German one, and then it closed. The Cooper old-timers held their last reunion. The engines kept running. There is something worth sitting with in that. The machines that built the modern world have a habit of outlasting the organizations that built them, quietly, in compressor stations, at 300 revolutions per minute, 24 hours a day, 7 days a week, whether anyone remembers them or not. That is not a metaphor. That is just what they do. And that is the story of the Cooper-Bessemer GMV. still can't get over the fact that engines built in the 1940s are out there right now tonight, pushing gas through American pipelines. If you have seen one of these running in person, drop it in the comments, where it is, what condition it is in, and if you made it this far, go ahead and subscribe. We do this every week.